Hello everyone, welcome back. So in today's video, we'll take up some more mechanics problems. And the first problem is from rotational motion, you could say. So let's read the problem statement. So we have two identical billiard balls. So we have to treat them like solid spheres, right? And they're moving with a speed of 3 meter per second and they're rolling without slipping towards each other on a horizontal rectangular U-shaped trough that is sufficiently deep that the balls are clear of its base. Okay, so now the diagram makes it look as if the balls are rolling on an incline, but it's a horizontal plane. Okay, but at the same time, the base of the ball doesn't touch the base of the U-shaped trough. Okay, so the side view will look something like this. This is how the base will look like. Okay, so this is the trough and the ball is rolling like this and the ball's base is above the bottom of the trough. Okay, now the resulting instantaneous collision is perfectly elastic and during it each ball reverses its linear velocity though their angular velocities are not affected. So r is the radii of the ball, so assume length of u shape is sufficiently large and the question is how wide does the trough need to be for the balls to collide twice. Okay, so initially they're approaching each other, they collide and their velocities are reversed, but the omega is still in the same sense. Okay, so we have to comment on the width such that the balls collide once again. Okay, so give this problem a try, guys, then check out the solution. Okay guys, so this is the rough diagram of the side view. Okay, so the dotted lines represents the part that is not visible to us, right? Okay, so this is the initial situation where the balls were approaching each other. Now right after collision, what happens is that the velocity vectors are reversed. Okay, and they are moving in the opposite sense. So this is the configuration just after collision and the angular velocities were given to be unchanged after collision. Okay, so now before we jump into the question, let's observe the spheres from the left side. Okay, so we are observing the situation from the side now. Okay, so this is how the picture looks from the side. Okay, so first let's mark down the direction of angular velocity. So if you look at this picture, if you curl your fingers in the direction of omega, the omega vector will point into the plane, right? So from the side view, so let's say the omega vector is towards the left in this case, which basically means the ball is rotating in the clockwise sense if we view it from the right side, right? Okay, so now the velocity of the center of the sphere, it'll be into the page. So this is basically the condition before the collision happened. Okay, this was when the ball was still rolling. So the ball was moving into the plane and it was rotating in the clockwise sense as viewed from the right side. Okay, so now if you observe something, these 2 points over here that I'm marking with a black dot represents the contact points. Okay, and while the sphere was rolling, these 2 points have to be at rest. Okay, so now let's try to write down the velocity of these contact points. So first, because of the translation of the sphere, it will have a velocity of v into the page, right? And then it will have a rotational component which is omega multiplied by the distance from the axis. So the distance from the axis, let's say it is equal to y. So the rotational component will be omega times y in the outward direction. Okay, so now as the ball is rolling without slipping, we can say v should be equal to omega y. Okay, so this is equation number 1. Let's try to complete this triangle. Okay, so the hypotenuse is equal to the radii of the sphere, right? And this length, if you observe, it is half the width of the trough, right? So this complete length, let's just take it as w. So this length is going to be w by 2. So yeah, this is the side view of the situation. Now, if you observe, this point should also be at rest, right? Now, if you connect these 2 points, this will actually give you the instantaneous axis of rotation, and basically all the points that lie on this axis will be instantaneously at rest. And the explanation for that is exactly the same as what we did for this point over here. So the rotational speed of each of the points lying on this axis is equal to omega y, and v and omega y are cancel each other. So all points lying on this horizontal line will have zero velocity. So now what happens is after the collision, the direction of velocity vector reverses, right? So now the velocity changes from x to dot. Okay, so now to the outward direction and its magnitude is still the same. So now if you observe, the points that were initially at rest will now start slipping, right? So now the ball is not rolling anymore, and that we can see from the side view as well, right? So The ball has a translational speed v, and the rotational speed is also omega y in this direction. So the contact point will have a speed of v plus omega y. So the ball will start slipping against the trough. Okay, so now the main goal in this question is that we want the balls to collide once again, right? Okay, so now kinetic friction will start acting and decelerating the balls, and there will come a point in the future where the velocity of the center becomes zero, right? In this situation, if the imagine that the angular velocity is in the counterclockwise direction, if this is the case, right, then what will happen is the ball will roll backwards and then they'll come collide once again, right? So that is basically what we'll be doing. So if you want the ball to collide once again, when the velocity of the center becomes zero, we'll just ensure that the angular velocity is counterclockwise. And similarly, it is in the clockwise sense for the other ball. In that case, the balls will approach each other once again and then they'll collide once again. Okay, so that's the main idea that we'll be focusing on. So let's see how friction force is acting first. So the force of normal will pass through the center of the sphere, and the force of friction, as the ball is coming out of the page, the friction will be acting in the inward direction, right? And its magnitude will be equal to mu times the normal reaction, right? And similarly, a friction force will act on the other point as well, right? Whose magnitude will be equal to mu times the normal reaction. Okay, so now let's just take the side view of the situation, right? So from here, we can see that the contact point is somewhere over here and it is slipping towards the left, right? So if I want to mark the friction, the total friction, I'm just going to call it as F, right? And this F is including both the contact points. I'm just directly writing it as F. So this F will actually decrease the omega and it will decrease and it will decelerate the center, right? Now we are interested in the situation when the velocity of the center of mass becomes zero. Okay, and in this situation, let's say the omega is omega dash in the clockwise sense. After this instant, what will happen is friction will start accelerating the center of mass and once again decelerating the omega dash, and there will come a point where they will start rolling again such that omega equals v by r, right? I'm going to call it as omega double prime. So, and after that instant, the sphere will start rolling and both the spheres will come collide. So basically, all we have to do is ensure that this omega dash is a positive quantity, right? So now let's try to apply some equations. So firstly, we can see that the center of mass's velocity became zero, and the only force that is accelerating or decelerating it is friction. So we can say that the impulse of friction, F dt, integrated from the time, let's say this is t equal to 0 and this is, let's say, t equal to some delta t. So if I integrate it from t equal to 0 to delta t, this should be equal to change in momentum, change in linear momentum of the center of mass, right? This should be equal to minus mv, but I'm just taking into account the magnitude. Okay, so this will be equal to m times v. So this equation is basically impulse momentum equation. Okay, so now we'll observe the angular momentum equation. So let's apply the equation about this horizontal axis passing through the center of mass. Okay, so this particular axis is what I'm talking about. So from the side view, this central axis is what I'm talking about. So with respect to this axis, the torque of the friction force is equal to the magnitude times this distance, which is y, right? So from the other view, friction force, if you observe this friction force, its magnitude is mu n. The torque of this friction about the horizontal axis will be friction force F times this distance y. So the angular impulse of friction is integral of F times y times dt, right? And this is once again integrated from 0 to delta t. So this will be equal to the change in angular momentum. Okay, so just by visually observing the situation, we can see that the friction is trying to decrease the omega, right? So the final omega will be less than the initial omega. So the angular impulse of friction will be equal to, in terms of magnitude, it will be equal to the moment of inertia about the central axis times initial omega minus final omega, right? If this equation confuses you, then all you can do is like write the equations with k cap and minus k cap. Okay, so for example, the impulse of friction, the angular impulse of friction, right? It will be, if you do r cross f, it will come out of the page, right? So maybe put a minus k cap with this, and omega is in the k cap direction. So if you want to write the vector equation, then it'll be the angular impulse of friction, right? This will be equal to the change in angular momentum. So the change in L vector will be I omega dash minus omega, and put everything with signs. Or what you can do is, I know that the friction will actually reduce omega, so I wrote it. So I know omega dash is less than omega, so I wrote omega minus omega dash. Okay, so now what I can do is I can take out the y from the integral, because y is a constant, right? So and integral, and what I'm left with inside is integral of f dt, and integral of f dt is just mv. On the left hand side it'll become, so on the left hand side it'll become mvy. So I about the central axis for a solid sphere is 2 by 5 mr squared, and the omega we earlier figured out, it was equal to v divided by y minus omega dash. Okay, so now the thing about omega dash is that, guys, we just want it to be greater than 0, right? So we'll solve for the inequality that omega dash should be greater than 0. So this just means 2 by 5 r squared times v divided by y should be greater than v times y, right? So the v cancels out, and we get y by r squared should be less than 2 by 5. Now y squared, we can write it as r squared minus w by 2 whole squared, right? So this will just become 1 minus w by 2r whole squared less than 2 by 5. And after solving the expression, we get the width should be at least greater than 2r times square root of 3 by 5. So that would be option B. Okay, so exactly, if the width is exactly equal to 2 root of 3 by 5r, then what will happen is, when the ball's center comes to rest, the omega dash which we solved for will also come to rest, right? So we want it to be greater than this value, so that there is some finite omega that brings them together. Okay, so now let's move to the next one. Okay, so this is the next problem. So we have two identical masses that are connected by a loose string as shown in the figure. Masses A and B are moving with velocity 2v and v on a smooth horizontal surface. So after sufficiently long time, so in the first question they're saying system of masses would have lost a kinetic energy of this magnitude only if the collision between A and B is perfectly inelastic. Okay, so first let's try to see what's happening. So initially, obviously the string won't play any role in the first part, right? So what will happen is A will start approaching B because it has a higher speed, and after collision their velocities will depend upon the type of collision, right? If it is perfectly inelastic, like what they're asking in the first question, then what will happen is, after collision, so this is block 1, let's say this is block 2, they'll both separate with the same velocity, right? So let's say the final velocity is vf. So now the thing is, if you want to find the loss in kinetic energy in the fastest way, I mean, one way is to just find out vf using momentum conservation, right? And then doing initial kinetic energy of the system minus final kinetic energy. But there is a way to directly write this if you observe this in the center of mass frame. Okay, guys, when you use this, you need to keep in mind something. The kinetic energy of any particle, right, it is a frame dependent quantity, right? Because the kinetic energy depends on the velocity, and the velocity is a frame dependent quantity, right? But when we talk about loss in kinetic energy, right, here in the case of collision, what happens when the kinetic energy is lost? What happens to the lost kinetic energy? It is emitted as heat or sound energy or something like that, and those kind of energies are frame independent. So that's why we can use the center of mass frame here. So that's the reason why we can observe with respect to the center of mass frame in this question. And it turns out that the energy that is lost in the center of mass frame, that we can figure out much easily, and that will also be the energy lost in the ground frame. Okay, so let's see what happens in the center of mass frame. So now here I'm going to use some results that I have derived in some earlier videos. But yeah, in short, basically for a two particle problem, right, like in this question, if you want to write the kinetic energy of the system in the center of mass frame, the result actually comes out to be half reduced mass times vrel squared. Okay, now this vrel is the difference in velocity vectors in the ground frame. So here in this question it will be 2v minus v, and if they were approaching each other, then it will be 2v minus v, which will become 3v. So vrel is the difference in velocity vectors in the ground frame. Okay, so I'm going to be, directly using this result, but the proof for this is also pretty simple. All you have to do is find the velocities of the particle in the center of mass frame and do half mv squared, right, for both the particles, and then you'll get this kinetic energy of the system in the center of mass frame. So yeah, that results actually, so, and it turns out the result is actually pretty neat. It is half mu vrl squared, and here the mu is actually the product of masses divided by their sum. Okay, so the initial kinetic energy, ke initial, now guys, both the masses are same, right? So their reduced mass just becomes m by 2. So it'll be half m by 2, and vrel is actually v, so it is v squared. So the initial kinetic energy is mv squared by 4. Now, if it is a perfectly inelastic collision, then what happens is both the masses have the same speed in the ground frame, right? So their center of mass will also move with vf. So with respect to the center of mass, both the masses will appear to be at rest. So if it is a perfectly inelastic collision, then what will happen is in the center of mass frame, both masses will have a final speed of 0. So which means the Ke final is actually 0. Okay, so there is no other forms of energy in this question. So the loss in kinetic energy in the center of mass frame is actually mv square by 4. So all the initial energy in the center of mass frame is converted into heat, sound, and other forms of energy losses, right? And this will be the same energy loss in the ground frame as well. So the system of masses would have lost a kinetic energy of magnitude mv square by 4 only if collision between A and B is perfectly inelastic. So yeah, if it is perfectly inelastic, then we know mv square by 4 will be lost. But is it the only case? And that is something that we have to read the other options as well, right? So that is something that we need to think about a bit more. So let's, we'll come back to that option. So let's read the other option. So in the second question, they're saying system of masses would not lose any kinetic energy if collision between A and B is elastic. So in option B there, we have to talk about some energy conservation stuff if the collision is elastic. Okay. And the third option, they're saying system of masses must have lost a kinetic energy mv square by 4 irrespective of nature of collision between A and B. And the D option says it has lost all its kinetic energy. Okay, so now we still haven't talked about the string, right? The role of the string in this problem. So now let's try to bring the string into the picture. Okay, guys, so before that, we know if the collision is elastic, if the collision is inelastic, we know they won't separate, right? After the collision, the masses won't separate. Like we know that, right? But if it was any other case, right, E is not equal to 0, then there will be some separation velocity between the masses, irrespective of what the value of E is. The only case in which there is no separation is inelastic collision. So basically, if E not equal to 0, then after collision, this guy will have some velocity, let's say V1, and let's say the string is loose for a bit, and the other mass will have some velocity V2, and definitely V2 will be greater than V1. Okay, so after collision, they'll start separating out. So after, some separation, there will come a point where the string becomes taut. So let's draw that situation. Okay, guys, so now the thing is, in this question, they didn't mention anything about the string, right? So we'll assume this is the usual ideal inextensible string that we usually work with. So if it's the ideal inextensible string, that means its length cannot change. But we know V2 is given to be greater than V1, right? The string, it cannot elongate anymore, right? So what will happen is large tensile forces will start originating in the string. It will decelerate the block on the front and it will accelerate the block coming from behind. The tensile forces will keep acting till the point where both the masses start moving with the same velocity. Okay. And once they reach the same velocity, now obviously the string length is going to be constant, right? And now there won't be any tensile forces. Now in the question, if they said that the string has a coefficient of restitution E, then the situation will be a bit different. Okay, so there is a problem in Pathfinder which deals with this, but here we'll take the ideal string approximation. So if it's the ideal string, then the tension will only act as long as the velocities at both ends become equal. And now if you observe something, the initial situation was the blocks moving with 2v and v. And finally, what ends up happening is that both the masses have the same separation velocity, just like the inelastic case, right? And in the inelastic case, we earlier figured out that the loss in kinetic energy is mv square by 4. So what happens is, let's say the collision is not inelastic, but and the blocks start separating. But the thing is, then the tension forces will make sure that finally both of the blocks attain the same speed. Indirectly, it still behaves like an inelastic collision, irrespective of what kind of collision it is. And therefore, the answer to this question will be option C. The system will definitely lose mv square by 4 irrespective of the nature of collision between A and B. I mean, we can also find this velocity v dash, right? All we had to do is momentum conservation between initial and final state. We can find that as well. Obviously, the system won't lose all its kinetic energy. And in option B, they're saying if it is elastic, there won't be any loss in kinetic energy. That's not true. Even if the collision is elastic, the energy loss is going to be mv square by 4. So even option B is wrong. And also option A will be wrong, because here they're saying the system will lose kinetic energy of mv square by 4 only if it is a perfectly inelastic collision. That's not true. Only makes it wrong. Okay, so that was the discussion for this question. That's it for this video, guys. If you enjoyed the video, please do like, share, and subscribe. And yeah, that's it. Thanks for watching.